Lecture we will be discussing about some sequence data, and we will learn how we do some models for sequence data. There are a lot of different sequence data available. For example, we have language data, then DNA data. Also, we have video data, just like stock price data or our voice data. These are typical examples of sequence data, but our main focus will be learning how do we process and model DNA sequence data. But we'll also learn some NLP or natural language processing tasks, because they have a lot of similarities. We have a couple of students from the health science background, so they are familiar with DNA data, but I think you will be quickly able to understand the language data if you haven't have any experience before, and the other ways as well. If you have experience in language data, you will be able to connect to the DNA sequencing data, because they have similarities as we will see. So there are a lot of important natural language processing tasks that people are working all over the world. For example, the machine translation, then the question answering, sentiment classification, document summarization, and the standard DNA classification tasks that you guys are already aware of that. So we'll take one example from each group, the document classification from NLP, and then DNA classification from DNA sequencing domain. And we'll see how things are quite similar and how we can model both problems, okay? If you recall, for our table of data, we learned the one-hot encode, and then there are other encodings as well. For example, the level encoding. For the DNA sequencing or in natural language processing tasks, we have again many other encoding techniques, and today we'll be mainly focusing on count vectorizer. So by the end of this lecture, you will be able to understand what count vectorizer is and how you use this to model both these tasks, document classification and DNA classification. Okay. So let's start with the general idea of count vectorizer. So for example, I will take one of the natural language processing tasks, for example, document classification, to explain the concept, and I will try to connect with the DNA sequence. So let's assume that we have a document D1, and there is only one sentence in the document, a black cat. Okay. So this is our document D1, and we have three words, a, black, and cat. And if you want to actually formulate in terms of numeric data for our encoding purposes, then we can just saying that we have a one time, black one time, and cat one times. Okay, so this is our count vector representation of the document D1. Okay, let's try to add another document. The second document is a white cat. Okay, we'll use the term word or token as synonymous, because sometimes you will see not every token or a substring ends up with a real word. So here we have added the document D2, and then we have added one more token, white, and the first document encoding now became, we have a one time, black one time, cat one time, but there is no white in a token in the first document. In the second document, we have a one time, no black word or token, cat one time, and white one time. Okay. Now we add the third document. The content is a black cat is as beautiful as a white cat. Okay. So now we have like bunch of new words came, So we have is, as, beautiful. But if you count the number of occurrence of each word or token in document D3, then we are saying that a occurred two times. Here is an A and here is an A. And then black one times, cat one times, white one times, is two times. A black cat is, and is one time, it should be one here. But as appeared two times, as and as, so as will be two times and beautiful one time. Okay. So the general idea of count vectorizer is how many number of token occurrences you have in a document. So for example, first document you had just only one a, one black, and one cat, and the rest are zeros. And the third document has a two times, as two times, and the rest are actually one time. So the count vectorizer actually encodes the number of occurrences of each word in the or token in the document. Okay. One thing is good with this representation here is because we have variable number of tokens in each document, but as you see that it turned out to be a uniform definition in terms of a numeric encoding, So in summary, the count vectorizer actually encodes the number of occurrences of each word or token in a document. Okay, so now we have 3 documents. So you will hear the term corpus. So we collectively call all these 3 documents as a corpus. Okay, and there is a dictionary. For example, all the words or tokens are my dictionary items, just like we have a dictionary for each language, English dictionary or French dictionary or other language dictionaries. Okay, so you can see that we have a few determiners, and then there are some nouns, and then some adjectives. So this is a perfect example of a linguistic dictionary. Okay. Now we will spend a little bit time to understand the concept of other terminologies. For example, unigram. Unigram is when you have each word is independent, just like the content in our dictionary. Okay, but if you extend it to bigram, because bigram is how actually you are extending your dictionary definition by not only including tokens or words, but all the pair of tokens that occur in your corpus. For example, here we have a black and then black cat. You see, like for the first document, you have 2 pairs, a black and black cat. So you have 3 tokens and 2 bigrams, a black and black cat. So this is how you actually extend from unigram to bigram. And if you pay a little bit more attention for the linguistic task, there are like some inherent explanation for that. If you see that a black cat is a valid English construct, but if I ask a cat black, so you might see that, oh, this is not usual, So this is how we actually encode syntactic information as statistical information. And there are some reasons, as you understand, that some of the pairs are more occurring than the others. And it is language dependent. For example, in English, we say black cat, but the French people actually swap the orientation, So they first say a cat and then they say black. Okay. So bigrams actually can capture some additional information than unigram. One thing is that if you add bigram, your dictionary definition will actually increase, and we'll see through our notebook presentation. Okay, so that is the whole idea of count vectorizer. Now we move to how we actually propagate the same idea for the DNA sequencing, because if you understand the encoding, then the rest are the same pipeline we can use for classification task, because our end goal is to actually learn a document classifier for certain NLP data and for sequence classification for some DNA data. Okay. If you are not familiar with DNA sequence data, in summary, every organism has cells, and in the cell they have certain protein patterns usually, so that really follow certain format. And in simple terms, we can say that the DNA sequence is a sequence of string alignments that people have done. For example, here we see a DNA diagram and a sequence of characters. So this is an example of a DNA sequence data, But let's assume that these are actually some sequence of characters, and just like our natural language, the characters here actually are predefined, So we have a predefined set of characters, So that constructs TC, then AZ, and maybe one more that we'll see in the coming slides. Okay. And length of DNA sequence actually varies. So for example, here we have 2 different DNA sequence as samples, and we can see that the first DNA sequence has like 390 characters as length, and the second one has a little bit longer definition of DNA sequence. Okay. So in summary, what we are trying to say that this looks to be quite similar to documents, but here there is no separation of words or tokens by spaces, but I think there are certain languages in the world, the Chinese and Thai language, they don't have the concept of spaces just like we have in the European languages, where you have a separation of words by a space, So anyway, we can correlate these two examples with documents, and our goal will be to identify white spaces, And we will use the count vectorizer, but using certain techniques. And one of the technique, what we call k-mer counting. So let's try to understand what is k-mer counting here. K-mer counting is you just split your sequence by overlapping subsequence. So, let's say this is the input sequence, and I ask this piece of code to give me all the overlap subsequence of length 5. So you can see that the first subsequent will be GTGCC. The next one would be TGCCC, and you go on and on. So by k-mer counting, we are just identifying all the overlapping subsequences of the same length 5, for example, here. So this will give me kind of identifying the tokens within this string, and that will simplify a sequence just like the words in the natural language. Okay. So you can see that for this sequence, we have converted into a document with 1, 2, 3, 4, 5, 6, 7 words or tokens. So now our data is quite aligned with the document data that we have, and we can use the same count vectorizer to find out that how many words are within a document, how many tokens are within a string, and use the same format as we have used here to encode our DNA sequence. So that was all about this part of the presentation. Now I will be moving toward presenting 2 notebooks, one for document classification and one for DNA sequence classification. And I will put all the notebook links with this presentation, so you can go and look at and run the code by yourself and try to understand the content. Okay, thank you so much.